Okay, so we're here with 3.5, all of the questions for foundation that's ever been in WJC. There's the formula sheet, and we're going to be sort of focusing on this one mainly. This one might pop up from time to time, which is speed equals distance over time, but I'll put that down by there. And first question, so this is probably, because it's question 6, it's going to be the start of the higher paper here, but even though this is foundation, because there's a crossover. How many waves are shown between A and C? So if I do this, so there's 1 complete wave to the dot, 2 to there, and then 2.5 to there. So a wave, pretty much, you need to go up, then back down, and then it starts again. Even though the amplitude's different, it's still a wave, and that's your second wave, and then half a wave there, so 2.5. Between which 2 points, A, B, C, D, E, and F, is the wavelength the longest? Well, I'm going to say between A and B again, because a wavelength for one wave is the distance there between B. You can see the distance between B and C is quite short. So if you was to get a ruler and measure these out, E to F might be a contender, but there's 1.5 waves between E and F. So the actual wavelength comes to there, so that's much shorter than A and B. The amplitude is the smallest. That's really obvious. That's B and C, between B and C, because the height of the wave is smaller. The 8 waves between A and F cover a distance of 240 centimeters. Calculate the mean wavelength. Well, if there's 8 wavelengths covering 240, the mean wavelength is 30 centimeters each one. And to check yourself there, you can think, well, I've got 30 centimeters for each wave. I've got 8 waves. Let's times all those together. I'm going to come up with 240. The diagram shows a transverse wave. To describe what is meant by a transverse wave. The energy of the wave moves at right angles, 90 degrees to the direction of the wave. So if I'm going up and down, then the direction of the wave is going to go this way then. Okay? But I'm moving it up and down like that. So that's 90 degrees to the direction of the wave. Here's another question. A teacher demonstrates water waves in a ripple tank. So this is one of your practicals. Diagram represents the waves. So state the wavelength of the waves. Now, a lot of people were struggling with this. Remember, you go down and then up and down, and we come to that point there, which is your wavelength 1.6. You could also go from peak to peak. So if you went from this peak to this peak, you could say 2.8 minus 1.2 is a wavelength. You can also go from trough to trough. So 2 minus 0.4 is also going to be 1.6. But like you can pretty much start a cycle of wave anywhere you wish to. But if it's starting at 0 anyway, you may as well just go like that, and it comes to 1.6. The amplitude is the maximum displacement. So here's the displacement. So 0, 0.5 is your displacement. So that's your amplitude. It's observed that 10 waves pass a point in 2 seconds. So if we know the frequency is the amount of waves that pass each second, and I got 10 waves in 2 seconds, then it's going to be 5 waves in 1 second. So it's 5 hertz. So 10 waves divided by 2 is going to be 5 hertz. Second equation from page 2 to calculate the wave speed. Well, let's have a look. Page 2. Wave speed, there it is. Okay, it's going to be equal wavelength times frequency. Well, we just worked out our frequency by there, and we know our wavelength from here. So we can just fill in the blanks. Now I've done a little triangle, V on top, because V pushes up top. Look. So you got, well, you can see what I've done there. It comes out to be 8 centimeters per second. So it stays in centimeters. We don't have to worry about converting too much. If it said meters per second, then we would have had to convert, but as it is, the distance is in centimeters. Very rare they'll trick you on that in a question like this. I'll warn you when they try and do things like that. And then you got this then, which is reflection. So the big thing to keep your eye on by here is the distance of these wavefronts. So the distance from there to there is the same distance from there to there, and you need to kind of approximately do the same distance coming back out, because they don't change. The wavefronts don't change. They would if it went through, if it was refraction. If it was going through this block, these would get tighter then. So the wavelengths become smaller because the speed of the wave changes in that medium. Next question then, which is the first question from a foundation paper, so this is going to be very easy, hopefully. Be careful here though, because they've got radio waves up this end and gamma rays down this end, so a little bit of confusion, trying to trick you. Red Martians invade Venus using X-ray guns. So red Martians invade. This is going to be infrared, and there's a question on that there. It's increasing wavelength, so the big wavelengths down the bottom, small wavelengths here, and therefore it's going to be increasing in frequency and decreasing in frequency down here. So they all EM waves are transverse waves, and they all move at the speed of light, which is 3 times 10 to the power 8. So in order for it to have a high frequency, there needs to be a low wavelength on them. So you've got lots of waves passing a point each second. Name the EM radiation labeled A. So I've said that's going to be your infrared. And then name the ionizing EM wave given out by some radioactive materials. Now, be forgiven for putting X-ray by here because it is ionizing, but the one you want, especially for radioactive materials, is gamma. That's just the symbol there. So it's a gamma ray. State why ionizing EM radiation is dangerous to humans: because they can mutate cells or they can damage cells. Okay, that's your top answer. I zoomed out a lot by here, haven't I? Let's put that back in. Let's bring this one up now. Again, this was like the first one on a higher. It says water waves on the sea are shallower than 1/20th of their wavelength. So I'm not going to read the question because the material. I always just like to get to the question, see what it's on about. So describe what is meant by a transverse wave. Well, we've had that already. The vibrations of the wave are at right angles, 90 degrees to the direction of the wave. So that was 2 marks. Use an equation from above. There he is, look, to complete the table below. So let's have a look at this table. Okay, so what's going on in this table? I've got the depth of the water. Okay, nice increments there. This is obviously my independent variable that I've chosen. Then I've got the distance there. And it's taking the square root. So this is the square root. So all my values here are the square root of this. Try not to get confused with that. It is what it is. So the square root of D is 0 there. The square root of D there is 0.71. So just keep that in mind a minute. Then you've got wave speed, which is meters per second, given it that. So I want you to fill in the blanks using that equation. Well, I've rewritten the equation. I always rewrite them. I don't know why. It just makes a lot of sense to me. This is your V. Okay, V's there. So if I want to know what a V is, then 3.13 times the square root of D. So this one was quite easy to get because you literally replace the square root of D there for 1.87. So this one is 1.87 times 3.13. Going to come up to 5.86. I don't know. I've complicated this, so don't look at this too much. I don't know why I've done the square root of 3. So I must have squared that to get 3.5. I don't know where I got 3.5 from. So ignore this. I'm going to draw a line through this one. Okay, this is the one you want to come out with 5.86. I should really adjust that on my sheet. This is the tricky one because you have to rearrange this formula. So I've always said if you see something together, always chuck this outside one on top in a triangle. So if you're looking for the square root of D, sorry, which I am by here, you need to put your finger over the square root of D. It's V on top of 3.13. My V is 3.83 that I got from there, right? And then that comes out to be 1.22. And that's that. Lovely? Happy. just pondering then. I was thinking about starting another video. Oh, I got more to the question anyway. So when depth changes from 1 to 4, the speed doubles from 3.13 to 6.26. So statement is true. The statement was, our Chris suggests that if the depth of the water increases 4 times, then the wave speed doubles. So what I've done there, gone to this table, and the depth of the water increases 4 times from there to there, look. Yeah, so it starts off at 1. If it increases 4 times, it goes to there. And it said, the statement, then the speed will double. Well, let's have a look if it does or not. So when the depth was 1, it was 3.13. When it was 4, 6.26. And I know that is double. I could do a little calculation, 3.13 times 2 if you want, but it's going to come up to 6.26. Then I've done my graph. This is worth 4 marks, my little graph by here. That's because there was no scale. So my biggest value on this one was like 6 point whatever it was I just said. So I've gone up to 7 in ones. So each small square is worth 0.1. And then I've gone up in 0.5 there along the bottom. And then I've plotted my results. I went wrong here. Should have done it in pencil. I could have rubbed it out. I've done the best curve I can. Maybe I was slightly off there, but I think that's a pretty good curve. And there's a question on that then on this page. Use your graph and the equation to calculate the wavelength of the water waves. There is a frequency of 0.2 hertz. So it's giving you your frequency. I just need to find, when it was 2 meters deep, what was my speed. You can see there 4.5. I'll show you how I got it. When I was at a depth of 2, it came and my wave speed was 4.5. And that's where I've got that from. And then when I put all the calculations together, because it's giving me the equation up here, it's going to be 22.5 meters. Chris now suggests that as the depth increases, the wavelength decreases. Okay, explain whether this statement is correct. Now you can see this is one of the last questions on the paper, so it's quite a tough question, but we'll have a go. I've said if the frequency is constant, this thing by here, right? As the speed increases, as this goes up, 4.5 maybe to 5.5 now, the wavelength will also increase, and I'll show you how to do that. Look, so instead of using 4.5, which I did by here, because that's what Chris is suggesting. He's suggesting if the depth increases, the wavelength decreases. Okay, so I'm going to chuck this up, because remember, depth is linked with your graph with your wave speed. Okay, so I'm actually going to make the, oh, I've got the wrong one there, wrong one. I'm going to make the wave speed higher, and then that comes out, the actual wavelength is longer, so the statement is not true. Okay, it says their wavelength decreases, well, actually gets bigger. So wavelength is increasing as the depth increases. But it is the last question on the exam. It is a tricky little fella, but totally doable if you understand my method there of, well, if it's saying that's 4.5, let's increase the speed, because I know that as I increase the speed by here, okay, then you're going to get more depth. So Chris is totally out of order. He doesn't know what he's on about. And I'm thinking we're going to start the next video on this question. So I put part 2. See you in a bit.